Vibration analysis understanding orders. Why orders matter, definition and frequency units. Orders are a fundamental concept in vibration analysis because they allow analysts to express vibration frequencies relative to the machine's running speed. Unlike absolute frequency units such as Hz Hz or cycles per minute, CPM, which change as machine speed varies, orders remain proportional to shaft speed. This consistency simplifies diagnosis and comparison across different operating conditions. For example, if a machine accelerates or decelerates, the peaks in a frequency spectrum shift along the x-axis when displayed in Hz, making it difficult to compare spectra over time. By converting these frequencies into orders, analysts can normalize the data so that 1x or 1 order always represents the shaft rotational speed, and higher multiples, 2x or 2 orders, 3x or 3 orders, etc., represent harmonics or other forcing frequencies. This approach is particularly useful for variable speed machines, where absolute frequency values fluctuate significantly. Orders also facilitate communication among analysts, as saying, high vibration at 3x or 3 orders, is universally understood, whereas quoting a frequency in Hz requires additional context. Furthermore, using orders enables accurate trending and alarm setting because normalized spectra align consistently, regardless of speed changes. In summary, orders provide clarity, consistency, and efficiency in vibration analysis, making them indispensable for diagnosing faults and monitoring machine health. An order is defined as the ratio of a vibration frequency to the machine's running speed. For instance, 1x corresponds to the shaft rotational speed, 2x or 2 orders is twice the shaft speed, and so forth. Orders can be integer multiples, such as 1x or 1 order, 2x or 2 orders, 3x or 3 orders, which typically indicate synchronous energy related to the shaft or coupled components, or fractional multiples, such as 6.1 orders or 3.09 orders, which often point to non-synchronous sources like bearing defects. Subsynchronous orders, those below 1x or 1 order, may indicate phenomena such as oil whirl or belt-related issues. Frequency can be expressed in 3 units, Hz Hz, cycles per minute, CPM, and orders. While Hz and CPM are absolute measures, orders are relative to shaft speed, making them more practical for diagnostic purposes. For example, a fan blade pass frequency might occur at 8x, meaning 8 times the shaft speed, regardless of whether the machine runs at 500 revolutions per minute or 3000 revolutions per minute. This relativity simplifies calculations and interpretation, especially when analyzing spectra from machines operating under varying speeds. Understanding these units and their relationships is critical for accurate vibration analysis and fault identification. Harmonics and peak families, synchronous, non-synchronous, and subsynchronous energy. Peaks in a vibration spectrum often exhibit relationships that reveal underlying mechanical conditions. Harmonics are a prime example. They are integer multiples of a fundamental frequency, typically the shaft running speed, 1x or 1 order. For instance, if the fundamental peak is at 1x or 1 order, harmonics will appear at 2x or 2 orders, 3x or 3 orders, and so on. These harmonic families indicate repetitive but non-sinusoidal vibration patterns, which commonly occur in conditions such as misalignment, looseness, or structural resonance. The presence of harmonics suggests that the vibration waveform is distorted, and the severity of the fault often correlates with the number and amplitude of these harmonics. In contrast, unrelated peaks that do not align with integer multiples of 1x may point to different sources, such as bearing defects or external influences. Visualizing spectra in orders rather than Hz makes these relationships immediately apparent, as harmonics align neatly at integer positions on the x-axis. This clarity aids in distinguishing between synchronous energy, which is tied to shaft rotation, and non-synchronous energy, which originates from other components. Recognizing these patterns is essential for accurate fault diagnosis and for determining whether observed vibration is due to a single source or multiple interacting factors. Let's see this diagram is the real, industry standard way to illustrate harmonics and peak families in vibration analysis, exactly as taught in Category 2 professional training and used in real diagnostics. Here's a technical explanation of what this diagram represents and why it is considered a real diagnostic illustration rather than a conceptual sketch. How this diagram represents real vibration data. Let's see the top plot, harmonics in an order spectrum. X-axis is an orders, normalized to shaft speed, y-axis is a vibration amplitude. What it shows is 1x or 1 order means shaft running speed, fundamental, 2x or 2 orders and 3x or 3 orders harmonics, integer multiples of 1x or 1 order. Green peaks form a harmonic family. Red peak is unrelated, non-harmonic. This pattern occurs in real machines when vibration is repetitive, distorted, non-sinusoidal. Common real-world causes are not limited to misalignment, mechanical looseness, shaft rub, structural resonance. No, let's see the bottom plot, peak families concept. This emphasizes relationship recognition, which is critical in Cat2 analysis. What analysts look for are equal spacing between peaks. Integer relationships, 1 order 2 order 3 order. Peaks that belong together. The bracket highlights a peak family, same forcing mechanism. Same mechanical origin. The red peak does not follow order spacing. Likely comes from bearings, external machinery, electrical sources, flow turbulence. This distinction is made daily in plant diagnostics. Spectral energy can be categorized into 3 main types based on its relationship to shaft speed: synchronous, non-synchronous, and subsynchronous. Synchronous energy consists of peaks at integer orders, such as 1x or 1 order, 2x or 2 orders, and 3x or 3 orders, and is typically associated with phenomena like unbalance, misalignment, and gear mesh frequencies. Non-synchronous energy appears at fractional orders, such as 6.1 orders or 3.09 orders, and often indicates bearing defects or other irregularities not directly tied to shaft rotation. Subsynchronous energy occurs below 1x or 1 order and may signal issues like oil whirl, belt resonance, or looseness. Understanding these categories helps analysts quickly narrow down potential fault sources. For example, a strong 1x peak usually points to unbalance, while multiple harmonics combined with elevated noise levels may suggest looseness. Non-integer peaks accompanied by sidebands often indicate bearing problems. By classifying peaks according to these categories and visualizing them in an order-normalized spectrum, analysts can efficiently interpret complex vibration data and prioritize corrective actions. Let's see this diagram. Here is a real, Category 2 vibration analysis, correct diagnostic diagram illustrating synchronous, non-synchronous, and subsynchronous energy, exactly as this concept is visualized and taught in professional vibration analysis. This type of diagram represents order-normalized vibration spectrum data, not conceptual artwork, and reflects how analysts interpret measured FFT results in the field. How to read this diagram or technical explanation. See the axes. X-axis is orders, normalized to shaft speed. Y-axis is vibration amplitude. This is how vibration software, SKF, Emerson CSI, Mobius, Brule and Kjaer, displays data once order normalization is applied. Synchronous energy, integer orders. These green peaks at 1x or 1 order, 2x or 2 orders, 3x or 3 orders. These are integer multiples of shaft speed. They are called synchronous energy. Directly tied to shaft rotation. Typical real causes. 1 order unbalance, 2 orders misalignment, 3 orders and higher harmonics looseness, distortion, resonance. Vibration analysis Category 2 rule for this is integer orders is shaft-related forcing. Now let's go to the next is non-synchronous energy or fractional orders. Red peak at a non-integer order, example 6.1x or 6.1 orders, it does not align with integer multiples. Moves independently of shaft rotation. Commonly modulated by 1x or 1 order sidebands, not shown here. Typical real causes: rolling element bearing defects, BPFO, BPFI, BSF, FTF. External excitation. Electrical or hydraulic interactions. Vibration analysis category 2 rule for this is fractional orders is non-synchronous sources. Now let's go to the next is subsynchronous energy, below 1x or below 1 order. Peak at 0.5x or 0.5 orders, below running speed, is defined as subsynchronous. It cannot be caused by normal shaft rotation. Typical real causes: oil whirl or oil whip from journal bearings. Belt resonance, severe looseness, fluid-induced instability. Vibration analysis category 2 rule for this is peaks below 1x or 1 order are always significant. Why is this diagram considered real? This diagram reflects measured vibration spectral behavior. FFT output after order normalization. Real diagnostic categories used daily in industry. Orders, harmonics, and energy categories do not exist physically, so the only valid, real, representation is a data domain spectrum, exactly like this one. Order normalization and software settings, practical benefits and diagnostic applications. Using orders effectively requires proper normalization of the vibration spectrum. Normalization ensures that the software correctly identifies the 1x or 1 order peak, which serves as the reference for all other orders. There are several methods to achieve this: using a tachometer during data collection, manually entering the machine speed, relying on software algorithms for automatic detection, or manually selecting a known peak in the spectrum. Tachometer input is the most accurate approach, as it provides real-time speed data. When manual selection is necessary, it is advisable to choose a high-order peak, such as a vane pass frequency, because resolution errors are minimized when dividing by a larger number. Once normalized, the spectrum can display peaks in terms of orders, allowing fault cursors and calculated bearing frequencies to align correctly. This process is critical for accurate diagnosis, trending, and alarm setting. Without normalization, the benefits of using orders, such as consistent comparison across speed changes and clear identification of forcing frequencies, cannot be fully realized. Orders provide numerous practical advantages in vibration analysis. They simplify the identification of fault-related frequencies by expressing them as multiples of running speed, making it easier to relate peaks to specific machine components. For example, a peak at 8x or 8 orders may correspond to a blade pass frequency, while a peak at 2x or 2 orders often indicates misalignment. Orders also enable analysts to overlay and compare spectra collected at different speeds, ensuring that patterns remain consistent despite operational variations. This capability is invaluable for trending, as it allows long-term monitoring of specific orders without the confusion caused by shifting frequency values. Additionally, orders facilitate clearer communication among analysts and maintenance personnel, as referencing high vibration at 3x or 3 orders is more intuitive than quoting absolute frequencies. In diagnostic applications, recognizing patterns such as harmonics, sidebands, and non-integer orders helps pinpoint issues like looseness, gear faults, and bearing defects. By leveraging orders, analysts can improve accuracy, efficiency, and confidence in their assessments, ultimately enhancing machine reliability and reducing downtime.